Hello guys, in this video I am going to explain about the bonding in coordination compounds. uh, First of all, let me explain about Valence Bond Theory, which can predict the geometry of a coordination compound or geometry of a complex around the central metal. So in coordination number, so we are going to deal with some coordination number. For example, we are going to deal about coordination number 4 and the coordination number 6, particularly in this video. In coordination number 4, there are two possibilities having hybridization sp3 and the sp2. sp3 hybridization means the geometry of the complex will be the tetrahedral geometry, which is drawn here. This is the geometry of the tetrahedral structure. And another hybridization possible for coordination number 4 is dsp2, which is square planar, in geometry. Okay, so square planar geometry is drawn here. So this is in the same plane, and this is particularly in case of 4D and 5D series elements. This can be tetrahedral geometry, can be from the 3D series, and then for 3D series elements the geometry can be square planar also. Let me explain in the following examples later in the next slide. And another coordination number that we are going to deal in this video is coordination number 6. In coordination number 6, two types of hybridization will be there: sp3d2 and d2 sp3. One in which d is written after sp3 and another one having written before the sp3, which means when this in this both this hybridization will have a geometry of octahedral. Both will have a geometry of octahedral. Octahedral geometry is here square planar, and one above and one below the plane. And in this sp3 d2 means if we use 5s, for example, in hybridization, 5s and 5p in hybridization, then if this 4d is used in hybridization, this will be inner orbital complex. And if I use 5s, 5p and 5d in hybridization, then this will give our outer orbital complex, this one, and this one is for 4d, for 5s, 6p, 5p. This is just an example. So it is written here, if sp3d2 is the hybridization, then this will be outer orbital complex, because the outer or the outermost d orbital will be used in hybridization. And if this is d2 sp3 hybridization, then the complex will be called inner orbital complex, and penultimate d orbital of the penultimate shell, means the shell which is just inside the outermost orbital will be used. For example, if 4s and 4p are used in hybridization, then the d orbital has to be from third shell, okay, 3d. So this hybridization will produce d2 sp3. d will be written first. So such complexes will be called inner orbital complex. I'm going to give examples of each these two hybridization. But first of all, let me go for coordination number 4. In coordination number 4, the possibilities, some common, not possibility, some common examples of complexes will be NiCl4 2 minus, NiCN4 2 minus. These two are same, but you know, Cl and Cn are different. Cl is a weak ligand while Cn cyanido is a strong ligand. So there will be differences in hybridization, and therefore their magnetic nature will also be different. And another one which is very common is NiCO4, where CO is carbonyl, which is also very strong ligand. In fact, this is the strongest ligand. Now, before discussing about these three complexes, let me give some hints about some ligands. These ligands are of two types. Some are weak and some are strong ligands. So example of some weak ligands are Cl, Br, water, and some strong ligands are Cn, Co, and NH3. So what uh, I'm going to tell is the functions of strong ligands. What can the strong ligands do? Okay, so if the ligand present is a strong ligand, then there will be pairing of electrons. There will be pairing of electrons. Means if there are unpaired electrons, if there are unpaired electrons like these two are unpaired in two different orbitals, then these two unpaired electrons will be getting paired up if the ligand is strong. In fact, by this valence bond theory, we cannot classify ligands according to their strengths. We are just using the strength of ligand from crystal field theory. Actually, with these functions of strong ligands, we can easily explain the valence bond theory actually. So here in this case okay, so here in this case, first function is what? Pairing of electrons, and the second function is excitation of electrons. Excitation of electrons means if this is 4, example 4s, and if electron is present in this orbital, and if it is 4p, for example, I'm just saying example, and 4s and 4p, they have different energy, and the 4p has higher energy than 4s. So going electron from here to here will be an excitation. So excitation of electrons will take place if the ligands are strong. And third function that I'm writing is involvement of n-1d orbitals in hybridization. In fact, I'm making these functions from my own so that we can explain the valence bond theory very easily with the help of these functions. So now let us go through this hybridization process. Nickel Cl42 minus has an oxidation state of +2 of nickel. So let me change the color. Okay, so in nickel, the electronic configuration is 4s2 and 3d, 4s2 and 3d 8. So for writing nickel 2 plus, we need to remove 2 electrons from 4s, not from 3d. So 4s will be 0, 4p is already 0, and 3d has an electron of and 3d has 8 electrons. This is represented here. 1 2 3 4 5 6 7 8 3 4 6 electrons are getting paired up, but 2 unpaired electrons are present in Ni2 plus. So what we need to check here is whether this Cl ligand is strong or weak. So Cl is a weak ligand, so pairing of electrons will not take place. Pairing of electrons will take place only in case of strong ligands. Okay, so in this case, no pairing of electrons will take place, but we need 4 empty hybrid orbitals, because number of coordinate bonds that are going to be formed is 4. So one 4s and one 4p orbitals will be getting hybridized to form 4 equivalent, exactly equal what sp3 hybrid orbitals. 2 unpaired electrons will remain as such, there will be no pairing of five these two electrons, because the ligand is a strong ligand. Sorry, the ligand is a weak ligand, so pairing of electron will not take place. So in this case, hybridization will be sp3. These two electrons are from what? Cl. These two electrons are also from Cl. These two electrons, all the 8 electrons are from the 4 Cl ligands. So the hybridization will be sp3. Geometry will be for sp3 hybridization. I have already told that geometry here in this case, the hybridization sp3 geometry will be tetrahedral. So the geometry is tetrahedral geometry. Magnetic nature is paramagnetic because there are two unpaired electrons here. There are two unpaired electrons, so we can calculate magnetic moment in this case, since there are unpaired electrons, and number of unpaired electrons in this case is 4. So so in this case, n will be 2, right? And when this is calculated, this value comes out to be 2 root 2 or 2.83, something like this, for magneton. So magnetic nature will be paramagnetic, right? And geometry is tetrahedral. Let me go to the second example. In this case, I am taking nickel Cn4 2 minus, or this example is very similar to this one, nickel NH3 4. The charge of the complex will be +2 here in this case. In both cases, the ligands are strong and the nickel has an oxidation state of +2 also in this case, right? So the electronic configuration is this. This is the electronic configuration. Now, since Cn is a strong ligand, these two unpaired electrons will be getting paired up, or ammonia is a strong ligand, so pairing of electrons will take place. But how many coordinate bonds will be formed? 4. So we need only 4 empty hybrid orbitals. So one will be D, and one is S, one is D, and one is S. So we need only 2 p empty orbital. So hybridization will be dsp2 hybridization. Okay, so when the hybridization is dsp2, geometry is what? Square planar. So magnetic nature of this complex will be diamagnetic because there is no unpaired electron present in this case. Number of unpaired electron is 0, so magnetic moment will also be 0. So geometry can be drawn like this. This is our nickel, and geometry is, square planar. Here Cn will be there, Cn, this is Cn, this will be Cn, and this will be Cn, like this. So this will be the geometry of the complex 2 minus, like this. Okay, let us go to the third example, in which nickel has a ligand carbonyl, which is the strongest ligand in fact, and it has an oxidation state of 0 because carbonyl is neutral ligand. So in this case, what happens is 4s has 2 electrons, and while 3d has 8 electrons, and the 4s and 3d, which one has higher energy? 3d. So since carbon monoxide is a strong ligand, these 2 electrons will be getting paired up, and 1d orbital will be vacant. But the 2 electrons from 4s, these 2 electrons from 4s, this will be shifted to this. Okay, so no d orbital, no 3d orbital will be available for hybridization. So this 4s will be empty, 4p orbitals were already empty, so hybridization will be sp3. So these 2 electrons, the d orbitals, which must be empty, are filled by the electrons from 4s. Okay, so 4s, 1 4s, and 3 4p orbitals will be getting hybridized to form sp3 hybrid orbitals, 4 sp3 hybrid orbitals. And these electrons which are written in blue color, they are coming from the ligands CO. Okay, so hybridization sp3 geometry will be tetrahedral and the magnetic nature will be diamagnetic, since no unpaired electron is present in the complex, right? So in the following slide, I am going to give some examples of complexes which are coordination number 4 only. See, for palladium and platinum complexes, and along with this I am going to give some examples of copper complexes also. So these three we have already discussed previously. So nickel Cl sp3 hybridization, tetrahedral geometry, paramagnetic nature, while Cn, nickel Cn4, Cn is a strong ligand, so hybridization was dsp2 square planar and diamagnetic nature, right? So in NiCO4, hybridization was what? sp3, tetrahedral and diamagnetic. Now this is the examples of the coordination number 4 complexes of 4D and 5D series. See, nickel, this nickel is in group 10 and this is 3D series, right? And palladium is in 4D series, group 10, and platinum likewise is in 5D series. So they are in the same what group, having equal number of valence electrons, so these are all similar. But what happens here is that in case of palladium and platinum, which are 4D and 5D series, the ligands are treated as strong ligands only. The ligands are treated as strong ligands only. The reason here is that uh, in their complexes, this can be explained in valence, not by valence bond theory. This can be explained in crystal field theory, where the splitting of d orbitals into different sets, okay, of orbitals will be large in their complexes, right? So therefore I'm just saying that with them the ligands will be treated as strong ligands only, because we are not going to discuss about the splitting of d orbitals according on the basis of the central metal. That is out of the syllabus actually. That is discussed in very higher classes. But for simplicity I'm just saying that with 4D and 5D complexes, the ligands will be treated as, and they can be treated as strong ligands. So their property will be exactly similar to this complex. Means what? This complex is what? Okay, this complex has the property that will also be possessed by these 4 complexes. Means nickel Cn4 has a hybridization of dsp2 and a geometry of square planar, and the magnetic nature was what? Diamagnetic. So all these 4 complexes will have a geometry of square planar, since their hybridization will be dsp2 like this complex, and their magnetic nature will be diamagnetic. Okay, so in the last I'm going to give information about these 2 complexes also. In this in this 2 example, copper has an oxidation state of +1 and a +2. +1 in this case, +1, the electronic configuration of copper plus is copper plus, right? Let me write here. Copper plus is 3d10, 4s0, 4p0. So there is no other option of hybridization other than sp3 in this case. in case of copper plus. But in case of copper 2 plus in this complex, so hybridization in this case was what? sp3, geometry will be tetrahedral, diamagnetic nature, non-paired electron is left. But in this complex, copper has an oxidation state of +2 since ammonia is neutral, right? So its electronic configuration will be what? For copper 2 plus, electronic configuration is what? 3d10. Now 3d10 can be explained, this is finished here, okay. 3d10 can be drawn like this. This is 3d 1 2 3 4 5, right? This is our 3d, and 10 electrons will be like this. These are the, sorry, 9 electrons, right? Copper 2 plus has an electron, okay, good here. Now copper 2 plus, how many electrons are there? 9, not 10, right? Only 9 electrons will be there. Let me write here copper 2 plus, wait, let me rough some portions here so that I have some space. Now this is copper 2 plus, and its electronic configuration is 3d9, not 10, okay. So 4s will be empty, 4p will be what? Empty. Now this is 3d, this is 3d in case of copper 2 plus, and this is what? 4s, and this is our 4p. This is 3d, this is 4s, and this is 4p. So 9 electrons is there. Let me change the color. Right, so 9 electron, 1 2 3 4 5 6 7 8 9. So there is one unpaired electron. So what happens here is that copper 2 plus, along with copper 2 plus, ammonia is the ligand, which is one of the strongest ligand. So since ammonia is a strong ligand, what happens is that this electron will be excited to one of the 4p orbitals, so that we have an empty what? 3d orbital. So this will be like this, this will be like this will remain as this, and this 3d orbital will be now vacant, and this electron is getting excited to this 4p orbitals, okay. So we have what? 1d, 1s, and a 2p. So hybridization will be dsp2, right? So copper NH342 plus will have a hybridization of dsp2, and the geometry will be what? Square planar. And what will be the magnetic nature of this complex? This will be paramagnetic, because there is one unpaired electron here, right? Okay, so in the next video, the coordination number 6, example of coordination number 6 will be discussed in the next video. For today, let me complete this video here. Please like and share this video, and if you are new to the channel, please subscribe to my channel. And if you have any question or any topic in chemistry where you want me to make video, please write in the comment box. I will definitely make video on that particular topic or question. Okay, thank you for today. Bye.